Welcome to Tech Explained. Today, we are covering a really complex but absolutely essential topic: security architecture, engineering, and operations.
Yeah, it's fundamental stuff.
It really is. It covers everything from, well, the very first design ideas all the way to the physical rooms where the tech actually sits. Our mission today is to unpack these core concepts, the principles, the controls, and pull out the knowledge that truly matters if you're working in modern security.
It's a big landscape, absolutely.
Yeah.
Touches on so many critical layers of how we protect things.
It does.
And, if you're designing systems or building them or maybe just running them day to day, you really need to get a handle on these concepts. We're looking at the blueprints, the architecture.
Okay.
How to actually build it securely, that's the engineering part.
Yeah.
Then the models that define what secure even looks like.
Right.
How we check security claims, the capabilities baked into systems, finding and fixing weaknesses, cryptography, of course.
Which is huge.
Oh yeah, massive. And then the physical environment too. Can't forget that.
Okay, so let's start right at the beginning then. Building secure foundations. That title itself, security architecture and engineering. What does that really break down to?
Well, architecture, right?
Yeah.
That word suggests a system, lots of interconnected parts, all working together for some purpose. Now, add security to that. What you're doing is applying policies, using knowledge, using experience to protect those parts and the whole system.
Yeah.
And you protect them based on how valuable they are. It's about the basic design and wrapping protection around it.
So the structure and then the security rules sort of layered on top.
Pretty much. And then engineering. That's the practical side. It's the systematic, step-by-step way you design and put those pieces together so they actually work securely.
Makes sense.
And a really, really key point here, something that comes up again and again, security, it's not an afterthought. You can't just bolt it on at the end.
Right.
It has to be part of every single phase, from the initial idea to building it, deploying it, running it, start to finish.
Build it in, don't bolt it on. Yeah, that seems crucial. So what's the core process driving all this secure design and building?
Well, whatever methods or frameworks you might use, the absolute heart of it is risk management.
Okay.
You have to start by figuring out your most valuable assets. What are you actually trying to protect? What matters most?
Identify the crown jewels.
Exactly. Then you identify the risks to those assets. What could go wrong? Who might attack them? What happens if they do?
The threats and vulnerabilities.
Right. And finally, based on the value, the likelihood, the impact, you decide which security controls make sense, which ones are appropriate and cost-effective to put in place to reduce those risks. You can't protect everything perfectly, so risk management helps you focus.
Prioritize based on value and risk. Got it. Now, to help make those design choices, there are some core philosophies, these essential secure design principles.
Yes, these are guiding ideas. They should really inform every decision you make when you're designing something secure. First up is threat modeling.
Threat modeling.
Okay, this means you proactively try to think like an attacker right from the design stage. You actively look for potential threats, potential vulnerabilities in the system's blueprint before you start coding or building.
Do it early.
Yeah, doing it early is way more efficient, way cheaper than finding and fixing fundamental flaws down the line.
Makes sense. Try to break it before you build it. What's another really core one?
Least privilege.
Yeah.
This is absolutely a cornerstone. Basically, any user, any process, any application, it should only have the absolute minimum permissions and access it needs to do its job. Nothing more.
Nothing extra.
Nope. Think about keys to a building. You only give someone the keys for the rooms they have to get into, not the master key for the whole place.
Right. Limits the damage if something goes wrong.
Exactly. If an account gets compromised, the damage is contained because it didn't have access to everything.
Okay. And defense in depth. I hear that one a lot.
You do, and for good reason. It means you never, ever rely on just one security control to protect something important.
Not putting all your eggs in one basket?
Precisely. You implement multiple layers of controls, different types of controls. So if one layer somehow fails or gets bypassed,
There's still something else.
yeah, there are other controls still there, ready to catch it.
Think of it like a castle. Multiple walls, maybe a moat, guards at different points, not just one strong gate. And this idea applies everywhere. Logical security, physical security, admin controls. We'll see it pop up again.
Multiple hurdles for an attacker. What about secure defaults?
This one's about making things safe right out of the box. Systems should ideally be configured in their most secure state by default.
So you don't have to fix it first.
Right. You shouldn't rely on the user or the admin to have to go in and change insecure initial settings. Default passwords, admin.
Oh yeah, terrible.
Or wide open network ports, services running that aren't needed. Attackers love those easy openings. The system should require a conscious choice to reduce security, not to enable it.
Make security the easy default path, okay?
Yeah.
Fail securely. What does that mean? This deals with what happens when things inevitably go wrong. A system crashes, an error occurs. It needs to fail in a way that doesn't suddenly create a security hole.
So the failure itself shouldn't be insecure.
Exactly. If, say, payment system crashes, it should just stop working safely, maybe show an error message. It shouldn't suddenly dump sensitive credit card numbers into a log file anyone can read. The failure state needs to maintain security.
Don't create a disaster during the breakdown. How about separation of duties?
This is key for preventing fraud and errors, especially insider threats. It means no single person should have the power to complete a critical task all by themselves.
You need 2 people.
Often, yes, or at least multiple steps involving different roles. It requires checks and balances. The classic example is requiring 2 signatures on large company checks. One person initiates, another approves. Prevents one person from doing something malicious or making a big mistake alone.
Spreading out the power. And keep it simple. Seems obvious, but
it's surprisingly important in security. Complexity is often the enemy. The more complex a system is, the harder it is to truly understand, the harder it is to secure properly, the harder it is to maintain.
And the more places for bugs to hide.
Exactly. Vulnerabilities love to hide in complex interactions. So this principle says, strip out unnecessary features, get rid of complicated configurations if you can. Focus only on what the system needs to do. Simpler systems are generally easier to secure.
Less surface area to attack. Makes sense. Now, zero trust. That's a really hot topic.
It is. And it's a pretty fundamental shift in thinking. Zero trust basically says, never automatically trust anything or anyone just because they're inside your network perimeter.
So being inside doesn't mean you're trusted?
Nope. Location doesn't grant trust. Every single access request from a user, a device, an application has to be strictly verified. Authenticated, authorized, checked against policy before access is granted. Every time. You assume breach, essentially.
Verify everything, trust nothing implicitly, but then there's also trust but verify. How does that fit?
They actually work together. Trust but verify comes after the initial zero trust style authentication and authorization. You verified the user is who they say they are. You've authorized their access based on policy. That's the trust part.
Okay.
But the verify part is crucial. It means you must continuously monitor what they're doing in real time. Are they staying within their allowed actions? Is their behavior normal or suspicious? It emphasizes the need for strong detection and response capabilities.
So zero trust for getting in, trust but verify for watching what happens next. Got it. How about privacy by design?
This one's about making privacy a core consideration right from the start. You build privacy protections into the system architecture itself, not try to tack them on later as an afterthought.
Embed privacy from the beginning. And finally, shared responsibility.
This is absolutely critical, especially with cloud services or any third-party provider. Security isn't solely the provider's job or solely your job. It's shared.
Who does what?
Exactly. You absolutely must have clear definitions, usually in contracts or agreements, outlining exactly which security tasks the provider handles, like securing the physical data center, and which ones you, the customer, are still responsible for, like configuring user access controls or securing your data.
Need to know your part and their part. Okay, that covers those core principles really well. Let's move on to security models and evaluation criteria. What exactly is a security model?
Well, think of security models as formal blueprints or rule sets. They describe what security should look like in a system or architecture. They give you a structured way to define and think about the security properties you want. And they've been around for a long time.
Setting the rules for how security should work conceptually.
Precisely. In big organizations, you hear about enterprise security architecture breaking down huge systems, protecting each part based on value. Frameworks like Zachman, Sevite, TOJAF help with that large-scale view.
Okay. Lattice-based and rule-based. Let's start with lattice-based.
Right. Lattice-based models use a structure of levels or layers, kind of like a ladder. They have strict rules about how information is allowed to flow between these different levels. The classic examples are Bell-LaPadula and Biba.
Okay, Bell-LaPadula first.
Bell-LaPadula. This one is all about confidentiality. Its only goal is preventing secrets from leaking out, stopping unauthorized disclosure.
How does it do that?
It has 2 main rules. First, the no read-up rule. You can't read information that's classified higher than your own clearance level. Simple enough.
Makes sense.
Second, the no write down rule. You can't write information from a higher classification level down to a lower one. This stops someone with top secret access from accidentally or intentionally copying that information into an unclassified document, for example.
Keep secrets contained by controlling reading up and writing down. Okay. And Biba.
Biba is the flip side. It focuses only on integrity. Its goal is preventing unauthorized modification of data, making sure data doesn't get corrupted or changed improperly.
So the opposite focus from Bell-LaPadula.
Exactly. And its rules are essentially the inverse, the no read down rule. You can't read data from a lower integrity level. This stops you from being influenced by less trustworthy information. The no write up rule, you can't write data to a higher integrity level. This prevents low integrity data from contaminating high integrity data.
Don't let bad data mess up good data. So Bell-LaPadula for secrets, Biba for accuracy. What's the Lipner implementation mentioned?
Lipner isn't really a totally new model. It was an attempt, a practical implementation, to combine features from both Bell-LaPadula and Biba to try and achieve both confidentiality and integrity in one system.
Trying to get the best of both worlds. Okay, this leads to thinking about information flow and something called covert channels.
Right. Information flow is just tracking how data moves, where it's created, stored, used, shared, eventually destroyed. Understanding that flow helps find weak spots. Now, a covert channel, that's sneaky. It's an unintended communication path. Yeah, it allows information to leak out in a way the system designers never planned for. They often use legitimate system functions, but in an unexpected way. They can be really hard to spot, sometimes called secret channels.
Can you give an example?
Sure. A storage covert channel might use shared memory. Imagine one process writes sensitive data to a temporary spot in RAM, finishes, and then another, maybe less privileged process comes along later and reads that leftover data from the same spot.
Reading leftover data.
Exactly. Or a timing covert channel. This uses subtle differences in how long things take. Maybe a web server responds just a tiny bit faster if you try to log in with a valid username compared to an invalid one. An attacker could measure those tiny timing differences to figure out which usernames are real without even needing passwords.
Wow, that's subtle. Exploiting side effects. Okay, let's switch to rule-based models.
Okay, rule-based models work well based on rules. They define specific conditions under which subjects, like users or processes, are allowed to interact with objects like files or data.
Clark-Wilson comes up as a key integrity model. How is it different from Biba?
Clark-Wilson is really important for integrity because it goes further than Biba. Biba mainly stops unauthorized people from making changes. Clark-Wilson adds rules to stop authorized people from making bad or improper changes. It's also focused on maintaining the overall consistency of the system.
So it's not just about who can touch the data, but making sure they touch it correctly.
Precisely. It wants to ensure the system stays in a valid state. It uses a few key ideas. One is well-formed transactions, predefined operations that are certified to always keep the data consistent. Think of them as approved ways to change data.
Okay.
Another is separation of duties, which we talked about needing multiple people for critical tasks. And the third is the access triple, subject, program, object. This is key. It means a user subject can't just directly access data object. They have to go through an approved program, and that program enforces the rules and only performs those well-formed transactions.
The program acts as a controlled gatekeeper, enforcing integrity rules. Bet it. What about Brewer-Nash, the Chinese wall model?
The Brewer-Nash model, the Chinese wall. Its specific goal is preventing conflicts of interest.
Conflicts of interest, how?
Imagine you work for a consulting firm. You start working on a project for company A. The model then builds a wall, preventing you from accessing any confidential information about company B if company B is a competitor of company A. Once you access data in one conflict class, you're blocked from accessing data in competing classes.
So your past access restricts future access to avoid conflicts. Interesting. Graham Denning and Harrison Russo-Ullman are also mentioned briefly.
Yeah, those are other rule-based approaches. Graham Denning focuses on defining rules for how subjects can access objects and how access rights themselves can be managed. Harrison Russo-Ullman delves deeper into the integrity of those access rights and managing access permissions for groups.
Okay, so models give us the theory. But how do we actually know if a product we buy, say from a vendor, is as secure as they claim? That seems critical. This is where certification and accreditation come in.
Absolutely vital. How do you trust that firewall or OS? Certification is the technical deep dive. An independent body tests the product or system against specific security requirements and standards to see if it meets them.
The technical check.
Right. Then accreditation is the official sign-off from management. They look at the certification results, consider the risks in their specific environment, and formally approve the system for operation for a certain period. It's management accepting the residual risk.
Technical validation plus management approval. And for that to be meaningful, you need independent ways to measure security, right? Not just vendor claims.
Exactly. You need objective, standardized evaluation systems. That's where evaluation criteria come in. The first really big one was the U.S. Department of Defense's TCSEC, the Trusted Computer System Evaluation Criteria. Everyone called it the Orange Book because of its cover.
Part of that rainbow series of books, what did it measure?
The Orange Book defined different levels of trust, from D1, minimal protection, up to A1, verified design. A1 was the highest, but it had some major drawbacks. Its biggest limitation was that it focused almost entirely on confidentiality.
Only confidentiality, not integrity or availability.
Mostly just confidentiality. And the other big issue was it was designed for evaluating single, standalone computers. It didn't really handle network systems well, which is, pretty much everything today.
Yeah, pretty big limitations now. So then came ITSEC.
Yes, ITSEC, the Information Technology Security Evaluation Criteria. This came out of Europe. It was an improvement because it could evaluate more than just confidentiality, and it was designed with networks in mind.
Better suited for modern systems.
Definitely. A key thing ITSEC did was separate the evaluation into two parts. Functionality, what the product does, using F levels, and assurance, how well it's tested, using E levels from E0 up to E6. Higher E levels meant more rigorous testing, maybe even looking at the source code.
Separating what it claims to do from how thoroughly it was checked, and ITSEC was eventually replaced by the Common Criteria.
That's right. Common Criteria, or CC, which is also an ISO standard, ISO 15408. This is the big one now, used internationally. It came about because multiple countries agreed to work together on one common standard.
Makes sense to have a global standard. How does Common Criteria work? What are the pieces?
Okay, there are three key components you need to know. First, the protection profile, PP. This is usually created by a user community, like government agencies or industry groups. It describes the security requirements for a whole category of products. Like a PP for firewalls might say all firewalls should support VPNs, logging, certain types of access control, etc.
A generic shopping list for a product type.
Sort of, yeah. Second, the target of evaluation, TOE. That's the specific product being tested. So Vendor X's Super Firewall version 3.0, that's the TOE.
The actual thing being evaluated.
Exactly. And third, the security target, ST. This is the document the vendor writes. It describes their TOE and makes claims about how it meets the requirements laid out in a specific protection profile. The vendor says, here's how our Super Firewall 3.0 fulfills the requirements of the firewall PP.
The vendor's specific claims about their product meeting the standard.
Right. Then the evaluation lab rigorously tests the TOE against the claims in the ST to verify if it actually does what the vendor says and provides the security functions at a certain level of assurance.
And Common Criteria uses these evaluation assurance levels, ELs.
Yes, ELs. They range from EL1 up to EL7. EL1 is just functionally tested. EL7 involves formal design verification, rigorous testing. It's the highest level of assurance.
So EL7 is always the best, right? You'd always want that.
You'd think so,
yeah.
But interestingly, no, not always. This is a really important point. EL7 isn't necessarily the best choice for a customer or even for the vendor to aim for.
Really? Why not? That seems backwards.
Well, achieving those very high ELs, especially EAL6 or EAL7, often means the product becomes incredibly complex.
Complexity again.
Yep. While it might be theoretically more secure according to the formal model, that complexity can make it really hard and expensive to configure correctly, manage day-to-day, and maintain in a real-world environment. If your security team can't actually manage the thing properly because it's too complex,
you might actually make it less secure through misconfiguration.
Exactly. Misconfigurations, unused features, things not being patched correctly because it's too hard, that can actually increase your real-world vulnerability. Most organizations tend to buy products certified up to maybe EAL4. An OS might be EAL3, a good firewall, perhaps EAL4. Vendors have to balance the security features with usability, performance, cost.
So peak theoretical security isn't always peak practical security.
That's a good way to put it. And another thing, a product's EL rating usually stays the same even after patches or minor updates, unless there's a major change in its fundamental security functions.
Good to know. Okay, we've covered principles, models, evaluations. Let's dig into the components within systems. Section 3. Understanding information systems security capabilities. Starting with the basics. Subjects and objects.
Yeah, fundamental concepts for access control. A subject is the active thing. It's trying to do something, access something. Could be a person logging in, a software process running, a program trying to read a file.
The actor.
Right. An object is the passive thing being acted upon, usually a file, a database record, maybe a printer, a server, even another process sometimes.
The thing being accessed. Got it. This leads to the reference monitor concept and the security kernel.
Okay, the reference monitor concept, or RMC, is an abstract idea, a core security principle. It says there must be some kind of conceptual gatekeeper that mediates every single attempt by a subject to access an object.
Every single one.
Every single one. This gatekeeper checks the rules, the security policy, decides whether to allow or deny access, and importantly, it has to log and monitor these attempts. It's the idea of a central, unavoidable checkpoint.
The theoretical security guard?
Kind of, yeah. Now, the security kernel is the actual implementation of that concept. It's the specific hardware, firmware, software component in the system that does the job of the reference monitor. It enforces the policy, mediates the access.
The real guard doing the checking.
Exactly. And for something to truly be a security kernel implementing the RMC, it needs 3 key properties. It must be complete. You can't bypass it. All access must go through it. It must be isolated. The kernel itself has to be protected from tampering, and it must be verifiable. You need to be able to confirm it's working correctly, usually through logs and monitoring.
Can't be bypassed, can't be tampered with, and you can check its work. Okay. And all these critical security parts together, they make up the trusted computing base.
That's right. The trusted computing base, TCB, is the sum total of everything in the system. Hardware, firmware, software that's responsible for enforcing the security policy. If any part of the TCB fails or is compromised, the whole system security is potentially undermined. It includes things like the CPU, memory, storage, firmware, the OS kernel.
Let's look at some of those TCB parts. Processors, CPUs, the brain.
The brain, exactly. Constantly cycling. Fetch instruction, decode it, execute it, store the result. From a security angle, a key feature is processor states or privilege levels.
Privilege levels.
Yeah, CPUs run in different modes, usually a high privilege mode, often called supervisor or kernel state, used for critical operating system functions. And a low privilege mode, problem or user state, where most applications run. This stops regular programs in user mode from doing things that could mess up the whole system, like directly accessing hardware or modifying critical OS data.
Restricting what code can do based on trust. How do CPUs help with process isolation?
Process isolation is super important. You don't want one application crashing and taking down others or reading another application's memory. The CPU helps with this. One way is time division multiplexing. The CPU rapidly switches between running different processes, giving each a tiny time slice. It looks like they're running at the same time, but they're kept separate in time.
Slicing up time.
Right. And the other big one is memory segmentation. The system carves up RAM into separate sections, and each process gets its own segment. The CPU and memory management unit enforce rules so that one process cannot normally access the memory belonging to another process. Keeps them in their own sandboxes.
Separate time, separate memory. Speaking of memory, the different types of storage.
Generally, we talk about 2 main types. Primary storage is the fast stuff, but it's usually volatile data disappears when the power goes off, and smaller capacity. Think CPU cache, CPU registers, and RAM.
Fast but temporary.
Exactly. Then secondary storage is slower, but its non-volatile data stays even when the power is off, and it holds much more. This is your hard drives, magnetic, SSDs, solid state, optical disks, CDs, DVDs, tapes.
Slower but permanent and large. Where does virtual memory fit?
Virtual memory, sometimes called paging. This is a trick operating systems use when they run out of physical RAM. They take a chunk of the hard drive space and use it as an extension of RAM, swapping data back and forth.
So it uses the hard drive like extra RAM.
Kind of. It stops the system from crashing when RAM is full, which is good. But accessing data that's been swapped out to the hard drive is much slower than accessing it directly from RAM.
Keeps it running, but with a performance hit.
Okay. You mentioned the system kernel earlier. How is that different from the security kernel? This seems important.
It is an important distinction. The system kernel is the absolute core of the operating system. It manages everything, hardware, processes, memory, file systems. It runs at the highest privilege level, like ring 0, which we'll get to, and has complete control.
The OS boss.
Pretty much. The security kernel, as we said, is the implementation of the reference monitor concept. Its job is specifically to mediate access requests based on the security policy. It might be part of the system kernel, or separate, but its focus is narrower, just enforcing security rules. Protecting the system kernel itself, using those CPU privilege levels, is absolutely critical.
System kernel manages the whole show. Security kernel is the focused access cop. Got it. This links back to privilege levels and the ring protection model. Yes. These are ways to structure trust within the software. The ring protection model is a conceptual way to visualize it. Imagine concentric rings. Ring 0 is the center, the most privileged, most trusted. This is where the system kernel, maybe some critical firmware, lives.
The inner sanctum.
Right. Then you have outer rings, like ring 3, which is the least privileged. This is where most user applications run. Code in an outer, less trusted ring can't just directly call code or access data in an inner, more trusted ring. It has to go through specific controlled interfaces or gates. Protects the core from buggy or malicious application code.
Layers of trust, protecting the center. What about firmware?
Firmware, that's the low-level software baked into hardware components that boots them up, gets them started. Think BIOS or UEFI on a computer.
The startup code.
Exactly. Now, historically, firmware was often read-only, hard-coded. But nowadays, a lot of firmware can be updated, which is good for fixing bugs or security holes in the firmware. But it also means
the hardware itself can be attacked by modifying the firmware.
Precisely. If someone can install malicious firmware, they could potentially compromise the hardware at a very fundamental level.
A deep level risk. And middleware. What's that?
Middleware. Think of it as software glue. It sits between different applications or systems and helps them talk to each other, especially if they weren't originally designed to work together. It acts as a translator or intermediary.
Connecting incompatible pieces. Okay. Abstraction and virtualization, huge concepts now.
Yeah, fundamental to modern computing. Abstraction is just the idea of hiding complexity. You interact with something simple without needing to know all the complicated details underneath. Driving a car, you use the steering wheel and pedals. You don't need to understand the engine combustion cycle.
Hiding the messy details.
Right. Virtualization is a powerful type of abstraction. It's about creating a virtual or simulated version of something, a server, a network, storage, an OS, to hide the underlying physical reality.
And the key piece of tech for this is the hypervisor.
Yes, the hypervisor. Also called a virtual machine manager, or VMM. This is the software layer that makes virtualization possible. It sits between the physical hardware and the virtual machines and allows multiple VMs to share the resources of that single physical machine.
The traffic cop for VMs?
Kind of, yeah. And the virtual machines, VMs themselves, are the emulated computers running on top of the hypervisor. Each VM runs its own full operating system, applications, everything. It thinks it has its own hardware.
Self-contained virtual computers.
Right. They're great for resource pooling, especially in the cloud, sharing hardware efficiently. And you can create standard golden images of VMs to deploy new servers really quickly. But that hypervisor, it's a really critical point.
If the hypervisor gets compromised,
you could potentially control all the VMs running on it. So securing and hardening the hypervisor itself is absolutely crucial.
High-value target. How are VMs different from containers? They sound similar.
They both involve virtualization, but at different levels. VMs are considered heavyweight. Each VM needs its own complete operating system, takes up more resources. Containers are lightweight. They share the host machine's operating system kernel.
Share the OS.
Yeah, through a containerization engine like Docker. A container just packages up an application and its direct dependencies. Because they don't need a full OS each, they're much smaller, start up faster, and are incredibly portable. You can run many containers on a single host OS.
VMs virtualize the hardware. Containers virtualize the OS for apps.
That's a good way to sum it up. And this ties into how applications are built. You have older monolithic apps, one big chunk of code. Or more modern microservices breaking the app into small, independent services talking over APIs. Containers are perfect for deploying microservices. And then there's serverless, or function as a service, FaaS, running even smaller snippets of code on demand. Containers as a service, TGS platforms, help manage containers at scale.
Breaking apps down. And woven through all this is layering, defense in depth again.
Absolutely. It keeps coming back because it's so fundamental. You need multiple security controls. And ideally, each control should do more than one thing, maybe prevent, detect, and help correct an issue. Don't rely on just one lock, one firewall, one anything.
Multiple layers, multiple functions. Lastly, in this section, trusted platform modules, TPMs.
Right, a trusted platform module, TPM. This is a dedicated security chip, usually right on the computer's motherboard. It follows an ISO standard, Its job is to provide hardware-based security functions. It acts as a hardware root of trust.
Hardware security anchor.
Yeah. It can perform crypto operations securely, like generating and storing keys. It can also measure the system state during boot up checking, the firmware, the bootloader, the OS, to make sure nothing has been tampered with. Provides platform integrity verification.
Checks for tampering at boot.
Exactly. And they're often designed as sort of a black box. You can send commands to the TPM, but getting sensitive information like private keys out is designed to be extremely difficult or impossible. Two key functions it enables are binding encrypting data, so only that specific TPM chip can decrypt it, and sealing tying decryption of data to specific hardware and software configuration measurements. The data only decrypts if the system state hasn't changed.
Linking secrets tightly to the specific hardware and its state. That's a solid overview of system capabilities. Let's move to Section 4, assessing and mitigating vulnerabilities. Finding and fixing the weak spots.
Right. Understanding common flaws is key to prevention and response. A big architectural one is the single point of failure, SPOF.
SPOF. That's when one thing breaking takes down the whole show.
Exactly. One component fails and a critical service or the entire system stops working. Think of a network with only one firewall or one internet router. If that device dies, connectivity is gone.
What's the fix?
Redundancy. You implement backup components. 2 firewalls, 2 routers, configured for high availability or failover, so if one fails, the other takes over automatically.
Building in spares for critical parts. What about bypass controls?
These are tricky. They are intentional ways to get around normal security procedures. Think of the factory reset button on your home router. It's there for a reason, right? If you lock yourself out.
Yeah, a recovery mechanism.
But it also completely bypasses the normal login security. The risk is these bypasses can be exploited if not managed carefully.
A necessary evil, potentially. How do you manage that risk?
You need compensating controls.
Right.
Maybe separation of duties. The person allowed to use the reset can't be the same person who then sets up the new configuration. Strong logging and monitoring to detect when these bypasses are used. And physical security stops someone unauthorized from just walking up and hitting the reset button.
Control and monitor the bypass. Okay. What's a TCTOU vulnerability? Time of use or race condition?
Talk to. Yeah. This happens when there's a tiny delay, a small window of time, between when the system checks if you're allowed to do something, time of check, and when it actually does the thing, time of use.
A gap between checking permission and doing the action.
Exactly. A malicious program might be able to slip in during that tiny gap and change something or perform the action itself after the check, but before the legitimate use. It's a race between the legitimate process and the malicious one.
Exploiting that timing gap. How do you stop that?
Primarily by minimizing that window. Check the permission again right before the action occurs. Make the check and the use as close to simultaneous as possible. Re-authenticate frequently.
Tighten up the timing. Let's talk about emanations. Sounds a bit sci-fi.
It does, a bit. Emanations are unintended signals leaking from electronic devices. Think electromagnetic radiation, maybe even sounds or heat patterns. Sensitive information being processed inside a computer can sometimes be picked up remotely by someone with specialized listening gear.
Like wirelessly snooping on what's on a screen.
That's the classic example, yeah. Van Eck freaking. Mitigation involves shielding. Using special Tempest-certified gear that limits emanations, or building shielded rooms, Faraday cages, using copper-lined walls, or even envelopes for sensitive documents. Other methods include emitting white noise, random electronic noise to mask the real signals, or creating control zones where unauthorized personnel or equipment simply aren't allowed near sensitive processing.
Shielding, noise, and distance. Okay. Let's cover a really basic but vital mitigation. Hardening.
Hardening is fundamental. It's the whole process of reducing a system's vulnerability by securing all its parts and shrinking its attack surface.
Attack surface.
That's basically all the different ways an attacker could potentially try to get in or interact with a system. Hardening aims to make that surface as small as possible. The guiding question is always, what is this system supposed to do? And then you disable or remove everything else.
Everything not absolutely essential for its job.
Exactly. If it's a web server, does it need FTP services running? Probably not. Disable them. Does a user's workstation need database server software installed? No. Uninstall it. Close unused network ports, apply patches, use host firewalls, encrypt disks, enforce strong passwords, set up good logging. It's a whole range of things. And always test afterwards to make sure you didn't break its main function.
Strip it down, lock it down. Mobile systems, phones, tablets, they seem inherently risky.
They really are. They get lost, they get stolen, they connect to untrusted Wi-Fi networks. Lots of risks. Mitigations involve a layered approach. Mobile device management, MDM solutions help manage the device itself, enforcing passcodes, encryption, allowing remote wipe if it's lost.
Controlling the device.
Right. And mobile application management, MAM, focuses on the apps and data on the device, maybe creating secure containers for work data, controlling which apps can be installed, whitelisting.
Controlling the apps and data.
Yep. Plus, you need strong policies, acceptable use, rules for bring your own device, BYOD, etc. User training is key. And a clear process for what happens immediately if a device is lost or stolen, who to notify, initiating that remote wipe. Secure remote access, like requiring VPNs and MFA, is also crucial. Endpoint security like anti-malware is needed too.
Lots of layers for devices out in the wild. The OWASP Mobile Top 10 is mentioned as a resource here.
Oh yeah, OWASP Foundation is fantastic. Their top 10 lists for web apps and mobile apps are essential reading. The Mobile Top 10 specifically lists the most common and critical security risks found in mobile apps. Things like insecure data storage on the device, insecure communication over the network, weak authentication, problems with cryptography, code quality issues. It's a great checklist for developers and security teams.
A go-to guide for mobile security risks. Okay, let's look at some different system architectures. Distributed systems.
Distributed systems are just systems where the parts are spread out, often across a network, and they communicate to work together. Think client-server apps, the internet itself, microservices. The main security challenge, a much bigger attack surface.
More places to attack.
Yeah. Every component connected to the network is a potential entry point. And if an attacker compromises one part, they might be able to move laterally to other parts of the system. Distributed file systems, DFS, where files are stored across multiple servers but look like they're in one place, add complexity around keeping data synchronized and controlling access consistently.
More moving parts, more potential openings. What about grid computing?
Grid computing is where you link up lots of computers, often powerful ones, to tackle a single, really large computational problem together, pooling their processing power.
Like scientific research simulations.
Exactly, that's a common use case. The risks here involve data integrity, making sure the computations across all those different machines are correct and haven't been tampered with. Data validation, preventing unauthorized use of the grid's power, making sure results aren't manipulated.
Securing the collective computation. Data warehouses seem useful, but risky.
Very useful for business intelligence. A data warehouse pulls data from lots of different sources across a company into one central repository, specifically designed for analysis and reporting. Makes it easier to see the big picture.
That's the risk.
It becomes a huge single point of failure. If the warehouse goes down, your reporting and analytics stop. And maybe more critically, it's a massive concentration of potentially sensitive data. If it gets breached, the attacker gets a whole lot of valuable information in one go. High-value target.
All the valuable data eggs in one basket. How is big data different?
Big data is similar in that it's about analyzing large data sets, but the material highlights three defining characteristics, the V's. Variety data comes from many different sources in many different formats, structured, unstructured. Volume, the sheer scale of data, often spanning multiple systems. And velocity, the data comes in quietly and often needs to be analyzed rapidly, maybe even in real time. Think social media feeds, sensor data, tools like Hadoop, MongoDB help manage this.
More diverse, much bigger, much faster data. And the goal for both warehouses and big data is often data mining and analytics using inference and aggregation.
Right. That's the point, finding insights, trends, patterns. Aggregation is just combining different pieces of data together. Inference is where it gets interesting from a security perspective. That's deducing information that isn't explicitly stated by combining or analyzing other available data.
Figuring out secrets from non-secret data.
Exactly. The risk is unauthorized inference. Someone figuring out something sensitive they shouldn't know by cleverly connecting the dots between less sensitive pieces of information. A mitigation technique mentioned is polyinstantiation.
Polyinstantiation.
Yeah, it's a database security concept. It basically allows the same piece of data, like the name of a project, to exist at different classification levels with different values. So someone with a lower clearance might see a cover name, while someone with higher clearance sees the real sensitive name. It helps prevent inference attacks based on what data is visible or not visible at certain levels.
Showing different truths based on clearance.
Yeah.
Okay, moving to critical infrastructure. Industrial control systems, ICS.
Industrial control systems, ICS. This is the umbrella term for systems that manage real-world industrial processes. Things like SCADA, supervisory control and data acquisition, DCS, distributed control systems. PLCs, programmable logic controllers. They run power plants, water treatment facilities, manufacturing lines.
High-stakes stuff. If these get hacked,
The consequences can be physical. Damage, disruption, safety risks, extremely serious.
what's the best way to protect them?
The gold standard discussed is air gapping. Physically isolating the ICS network completely, no connection to the internet, no connection to the corporate business network. If it's truly air-gapped, remote attacks become incredibly difficult.
Just cut it off from the outside world, but that's not always possible.
Often not. For operational reasons, remote monitoring, data collection, and patching these systems can be a nightmare. They're often old, run-critical processes you can't just take down for updates.
So if you can't air gap or patch easily,
You rely heavily on compensating controls, continuous, non-stop logging and monitoring, especially looking for anomalies, unusual network traffic, weird commands, regular vulnerability assessments focusing on any connections that do exist, strong network segmentation using VLANs or dedicated zones to limit how far an attacker can move if they do get in. Physical security is also paramount for ICS.
layers of monitoring and containment. How about the Internet of Things, IoT? Everything's connected now.
Internet of Things, IoT, smart thermostats, cameras, appliances, sensors, billions of them.
Yeah.
And honestly, security is often an afterthought in their design.
Built for convenience, not security.
Often seems that way. Many have weak or no security features, hard-coded default passwords, they're difficult or impossible to patch. This makes them easy targets for attackers, often getting roped into huge botnets for DDoS attacks.
Lots of weak points out there.
Mitigation really starts with being a smart consumer research before you buy. Then, careful setup, change default passwords immediately, put them on a separate network segment if you can, like a guest Wi-Fi network, and keep them updated if the manufacturer actually provides updates.
Be careful what you connect. Okay, cloud services. Huge topic. Models and security.
Cloud is everywhere. Can
Right.
be public, like AWS, Azure, Google Cloud, private, just for your organization, or hybrid, a mix. The key is understanding the shared responsibility model, which we touched on.
Right, knowing who handles what security tasks.
Exactly. And the common characteristics. On-demand service, network access, resource pooling, elasticity, scaling up, down, measured service, pay for what you use.
And the main service models. SaaS, fast.
SaaS, software as a service, is renting ready-to-use software. Use a web-based like Gmail or Salesforce. You manage users and data.
Like renting an apartment.
Good analogy. ISS, infrastructure as a service, is renting the basic building blocks, virtual servers, storage, networking. You install the OS, manage applications, data.
Like renting the land and building your own house.
Yeah. And PayS, platform as a service, is somewhere in between. The provider manages the infrastructure and the OS middleware. You just deploy and manage your applications and data.
Like renting a house where the landlord handles maintenance, you just furnish it.
Right. There's also KS, containers as a service for running containers, and FAS, function as a service for serverless code. The key takeaway across all models: you, the customer, are always ultimately accountable for your data security, even if you outsource the responsibility for securing the infrastructure.
Accountability stays with you. How do you protect data in the cloud?
Strong access controls, definitely. And encryption is critical. Encryption in transit, encryption at rest. A really strong best practice is to encrypt your sensitive data before it even leaves your premises and goes to the cloud. Encrypt locally first.
Encrypt before it goes up. What about managing identities in the cloud?
It's a challenge. You move from traditional on-prem directories, like Active Directory, often towards identity as a service, IDEA solutions. Technologies like SAMLA are used for exchanging authentication and authorization information between your system and the cloud provider or other services. Oath is commonly used for delegated authorization, allowing one service to access resources from another on your behalf securely.
Cloud identity tech. Migrating to the cloud benefits and risks.
Big benefit is often financial shifting from buying hardware upfront, CapEx, to paying ongoing subscription fees, OpEx. Big risk, vendor lock-in. Getting so tied into one provider's specific services that it becomes really difficult or expensive to ever move away. Requires careful planning and due diligence on the provider's offerings and security.
Plan your exit strategy before you go all in. How does forensics work in the cloud? Must be different.
It is definitely more complex. You're often dealing with virtual disk images, VM snapshots. Getting access to the evidence can depend heavily on the service model.
How so?
Well, in SaaS, you're almost entirely reliant on the provider for logs and data. In Pennywise, you might have access to your application logs, but neither provider for infrastructure logs. In IaaS, you have the most control you can usually get snapshots of your VMs, disks, maybe memory, but you might still need the provider's help for network traffic logs or hypervisor level information. And you still need those two bit-for-bit copies for evidence preservation.
Relying on the provider often. Okay, shooting gears to web-based vulnerabilities. Web apps are everywhere. Big attack vector.
Huge. They're often the main way users interact with backend data. 3 major vulns to know are cross-site scripting, XSS, cross-site request forgery, CSRF, and SQL injection.
Okay, XSS first. What is it? Who's the target?
Cross-site scripting, XSS. This is where an attacker manages to inject malicious script code, usually JavaScript, into a web page that other users then view. The key thing, the target of XSS is the victim's web browser. The malicious code runs in their browser, not on the server.
Makes the victim's browser run bad code.
Exactly. There are 2 main flavors, stored XSS or persistent. The bad code gets saved on the web server, maybe in a comment field or user profile. Then, every single user who visits that page gets the malicious scripts sent to their browser.
Stored on the site hits everyone.
Right. Reflected XSS or non-persistent, this is more common. The malicious script is part of a link, URL, that the attacker tricks the victim into clicking, maybe through phishing. The victim clicks, their browser sends the request to the vulnerable website, and the website reflects the script back in the response. The victim's browser then runs it. It's not stored on the server.
Sent via a link reflected back to the victim. What do attackers do with XSS?
Steal session cookies to hijack accounts, redirect users to malicious sites, install malware, lots of things.
Nasty. How is that different from CSRF?
Cross-site request forgery, CSRF, sometimes called CSRF. Here, the target is the web server, not the user's browser executing code. CSRF tricks a logged-in user's browser into sending a forged request to a website they're already authenticated to.
How does that work?
Okay, imagine you're logged into your online bank. An attacker crafts a malicious link or embeds something in a web page that, when you click or load it, sends a request to your bank's website, say, or a request to transfer money to the attacker's account. Because you're already logged in, your browser automatically includes your session cookies with that request. Your bank's server sees a valid request from a logged-in user and performs the action. You might not even know it happened.
Wow. So XSS runs code in my browser. CSRF makes my browser send commands to the server using my logged-in status.
That's the core difference, exactly. XSS exploits trust in the website content. CSRF exploits the website's trust in the user's browser session.
Okay. And the third big one, SQL injection.
SQL injection, school. This targets the database behind the web application. SQL is the language used to talk to databases. If a web application takes user input, like from a search box or login form, and directly sticks it into a database query without cleaning it first.
Cleaning it?
Validating it, making sure it doesn't contain malicious SQL commands. If it doesn't clean the input, an attacker can type SQL commands into the input field. The web application then sends these commands to the database, which executes them.
Like putting database commands in the username box.
Exactly. The classic example is typing something like OR11 into a password field. If a backend code just blindly combines strings, the resulting SQL query might become something like select from users, where username admin and password or 11. Since 11 is always true, the OR makes the whole condition true, and the database might log the attacker in as admin without needing the real password.
Tricking the database logic. How do you prevent squilly?
The absolute #1 defense is input validation. Never, ever trust user input. You have to rigorously check and sanitize everything before you use it in a database query. Server-side validation is crucial. Client-side checks in the browser are easily bypassed. Whitelist validation is best. Only allow input that matches a strict, predefined pattern. Do only numbers, only certain characters, specific length.
Be super strict about what input is allowed.
Yes. Other strong defenses are using prepared statements or parameterized queries. These programming techniques separate the SQL command structure from the user supply data, so the data is treated purely as data, not as executable code, preventing injection. Stored procedures can also help.
Separate the command from the data. Makes sense. And reducing risk overall for web vulns means hardening the web app itself.
Absolutely. Harden the web server, harden the application server, harden the application code, follow vendor guides, OWASP guides, industry best practices, minimize the attack surface, disable unused modules, patch everything, configure security settings properly.
Lock it down. Okay, that brings us to section 5, applying cryptography, a huge and critical area.
Huge, yes, and ancient. People have been using codes and ciphers for millennia. But the single most important thing about modern cryptography, honestly, is key management.
Key management, more important than the algorithms.
In practice, often yes. You can have the strongest algorithm in the world, but if your keys are weak or stolen or managed poorly, the whole system breaks down. How keys are generated, distributed, stored, used, rotated, destroyed, that's paramount.
The keys are the key. What security services does crypto actually give us?
It provides several really important services, sometimes individually, sometimes combined. Confidentiality, obviously keeping secret through encryption. Integrity, ensuring data hasn't been tampered with, often using hashing. Authenticity, verifying who sent the message or created data, usually with digital signatures. Non-repudiation, preventing someone from denying they did something, like sending a message. Non-repudiation of origin, or receiving one. Non-repudiation of delivery. And it provides access control, in a way, because only those with the right key can decrypt and access the information.
Confidentiality, integrity, authenticity, non-repudiation, access control. Quite a list. Let's get some basic terms straight. Plain text, ciphertext.
Okay. Plain text is your original readable message or data. You use a crypto system, which is the combination of a specific algorithm, the mathematical recipe, and a secret key to perform encryption. That transforms the plain text into ciphertext, which is the scrambled, unreadable version.
Plain text in, ciphertext out.
Right. Then, to get back to the original, you need decryption. You use a compatible crypto system, the same algorithm, and the correct key to turn the ciphertext back into plain text.
What about key space, work factor, confusion, diffusion, avalanche? These sound technical.
They are, but the concepts are important. Key space is just the total number of possible unique keys for a given algorithm based on its key length. A 2-bit key has a tiny key space, only 4 possibilities. A 256-bit key has an astronomically huge key space. Bigger key space generally means harder to guess the key.
More possibilities, harder to guess.
Right. Work factor is an estimate of how much time and effort it would take to break the crypto, usually by trying all possible keys, brute force. Confusion is a property that obscures the relationship between the key and the resulting ciphertext. Makes it hard to figure out the key, even if you have lots of ciphertext.
Hiding the key's influence.
Yeah. And diffusion spreads the influence of each single bit of the plaintext over many bits of the ciphertext. Change one letter in the plaintext, and the ciphertext should change dramatically all over. This is related to the avalanche effect. Small change in input, plaintext or key, causes a huge, unpredictable change in the output, ciphertext. These properties make cracking the code much harder.
Making patterns impossible to find. And stream versus block ciphers.
2 main ways ciphers operate on data. Stream ciphers encrypt data 1 bit or 1 byte at a time. They often use a keystream generator and XOR the keystream with the plaintext. They tend to be faster, good for real-time communication like voice or video.
Bit by bit, fast.
Block ciphers work on fixed-size chunks or blocks of data, maybe 64 bits or 128 bits at a time. They apply complex operations to each block. They're generally a bit slower because of the blocking and processing, but they offer different modes of operation like ECB, CBC, CTR that provide different security properties for handling sequences of blocks.
Chunk by chunk, different modes. Steganography and null ciphers, these aren't really encryption, are they?
Not in the sense of scrambling data. They're about hiding the fact that a message even exists. Steganography is hiding data within something else, like embedding a secret text file inside an image file or hiding data in the unused slack space within allocated file storage. The image looks normal, but it contains hidden data.
Hiding in plain sight.
Kind of. A null cipher is even simpler, hiding plain text within other plain text. Maybe the real message is formed by the first letter of each word or every third word in an otherwise innocent-looking paragraph.
Hiding messages within messages. Okay, let's compare the 2 main types of real cryptography, symmetric and asymmetric, starting with symmetric.
Symmetric cryptography. This is the classic approach. It uses a single shared secret key. The same key is used for both encrypting the plaintext and decrypting the ciphertext. Both the sender and receiver must have this exact same key, and they must keep it absolutely secret.
One key for both locking and unlocking. What are the pros and cons?
The big advantage is speed. Symmetric algorithms, like AES, are extremely fast and efficient. They're great for encrypting large amounts of data, like entire hard drives or large file transfers.
Very fast. What's the downside?
The huge downsides are key distribution and scalability. How do you securely get that shared secret key to the other person in the first place? You can't just email it, right? That's the key distribution problem. Often requires an out-of-band method, like sending it via courier, which isn't practical.
Getting the secret key there securely is hard.
Very. And scalability, if you have 100 people who all need to communicate securely with each other pairwise, you need thousands of unique keys. Managing all those keys becomes a nightmare. Also, symmetric crypto by itself doesn't provide authenticity or non-repudiation. How do you prove who sent the message if you both share the same key?
Fast for data, but key management is a major headache. This is where asymmetric comes in.
Exactly. Asymmetric cryptography, also called public key cryptography, was invented to solve these problems. It uses two keys, a mathematically related pair, a public key, and a private key.
Two keys instead of one.
Right. The public key can be shared with anyone, freely distributed. The private key must be kept absolutely secret by the owner. The magic is, data encrypted with the public key can only be decrypted with the corresponding private key. And data encrypted or signed with the private key can be verified with the corresponding public key.
Public key locks, private key unlocks, or private key signs, public key verifies. How does this fix the symmetric problems?
It solves key distribution beautifully. If I want to send you a secret message, I just need your public key, which you can post anywhere. I encrypt the message with your public key. Only you, with your private key, can decrypt it. No need to securely exchange a shared secret beforehand.
Much easier key exchange.
Way easier. And scalability is solved too. Each person just needs their own key pair. They can communicate securely with anyone whose public key they have. Plus, asymmetric crypto is the foundation for digital signatures, which give us authenticity, proving who sent something, and non-repudiation, they can't deny sending it.
How does it prove authenticity again?
Okay, say you want to prove a message came from you. You take the message, or usually a hash of it, and encrypt it with your private key. This creates a digital signature. Anyone can then use your public key to decrypt that signature. If it decrypts successfully and matches the message hash, they know it must have been signed by your private key because only you have it. Proof of origin.
Clever. What are the downsides of asymmetric? It sounds perfect.
The main drawback is speed. Asymmetric operations are much slower than symmetric ones, orders of magnitude slower. They also require significantly larger key sizes, like 2048 bits or more for RSA, to provide equivalent security to smaller symmetric keys like 128 or 256 bits for AES.
So much slower, needs bigger keys.
Yeah. It relies on hard math problems like factoring huge numbers, RSA, or the discrete logarithm problem on elliptic curves, ECC. These are easy to compute one way, multiplying primes, but incredibly hard to reverse, factoring the result. ECC is generally preferred now because it gives similar security with smaller keys and faster performance than RSA. Diffie-Hellman is another asymmetric algorithm, but it's primarily used just for securely exchanging a symmetric key, not for general encryption or signatures.
Okay, so symmetric is fast, but has key problems. Asymmetric solves key problems, but is slow. The solution?
Combine them. Hybrid cryptography. This is how most secure communication actually works, like TLS-SSL for websites.
Use both. How?
You use the slow asymmetric crypto just for the initial setup to securely exchange a symmetric session key. For example, the sender might generate a random symmetric key, encrypt the actual data with that fast symmetric key, and then encrypt the symmetric key itself using the recipient's public key.
And encrypt the fast key with the slow key's counterpart.
Exactly. You send the symmetrically encrypted data and the asymmetrically encrypted symmetric key. So the recipient uses their private key to decrypt the symmetric key, and then uses that fast symmetric key to decrypt the bulk data. Best of both worlds. Secure key exchange and fast data encryption.
Smart combination. Now, ensuring data integrity, we mentioned hashing.
Right. Hashing algorithms are essential for integrity. They take any input message, run it through a one-way mathematical function, and produce a fixed size output called a hash or digest.
Fixed size, one way?
Yep. Key properties. It's computationally infeasible to reverse. Get the message from the hash. It's deterministic. Same message always gives same hash. Tiny change in the message produces a completely different hash, avalanche effect. And it should be collision resistant. Very hard to find two different messages that produce the same hash.
So if the hash matches, the data hasn't changed.
Exactly. You calculate the hash of the data you send. The recipient calculates the hash of the data they receive. If the hashes match, the data integrity is verified. Popular strong algorithms today are the SHA-2 family, SHA-256, SHA-512, and the newer SHA-3. Older ones like ND5 and SHA-1 are considered weak and shouldn't be used for security purposes anymore due to collision vulnerabilities.
Use SHA-2 or SHA-3. How do digital signatures bring hashing and asymmetric crypto together?
Okay, a digital signature provides integrity, authenticity, and non-repudiation. Here's the process. The sender takes their message and hashes it, creating a message digest.
The fixed size hash.
Right. Then, the sender encrypts that hash digest using their own private key. That encrypted hash is the digital signature.
Encrypt the hash with the private key.
Yes. The signature is often sent along with the original message. The recipient receives both. They first calculate their own hash of the received message. Then they use the sender's public key to decrypt the received digital signature. This reveals the original hash calculated by the sender.
Decrypt the signature with the public key to get the sender's hash.
Correct. Finally, the recipient compares the hash they calculated themselves with the hash they decrypted from the signature. If they match, bingo.
What does the match prove?
It proves integrity, because the hash matches the message wasn't altered, and authenticity non-repudiation, because only the sender's private key could have created a signature that decrypts correctly with their public key. It ties the sender to that specific message content.
Very powerful, but how do I trust that the public key I'm using really belongs to the sender?
Excellent question. That's where digital certificates come in. A digital certificate is like a digital passport. It binds an identity, a person, a server, an organization to their public key.
Ties the key to the owner.
Exactly. And this binding is certified by a trusted third party called a certificate authority. Most certificates follow the X.509 standard format.
The CA vouches for the key ownership. How does that trust work?
It's based on a chain of trust. At the top, you have a root CA. This is a highly trusted entity whose own certificate is self-signed or trusted directly by your operating system or browser. This root CA might sign certificates for intermediate CAs, and those intermediate CAs sign certificates for issuing CAs. And finally, an issuing CA signs the certificate for the end entity, like a website or a person. Your system verifies this chain back to a trusted root.
A hierarchy of trust starting from the root. What if someone's private key gets stolen? That certificate is no longer trustworthy.
Correct. If a private key is compromised, the corresponding certificate must be revoked immediately. CAs maintain lists of revoked certificates. Keys and certs should also be replaced periodically anyway, before they expire as a best practice.
How do systems check if a certificate has been revoked?
Two main ways. The older method is the Certificate Revocation List, CRL. The CA publishes a signed list of all revoked certificate serial numbers. Your browser or system would have to download this potentially large list periodically.
Downloading a big list seems inefficient.
It can be. The more modern method is OCSP, Online Certificate Status Protocol. Your system sends a quick query directly to the CA's server or a designated responder asking, hey, is certificate serial number 123 still valid? It gets a direct yes/no answer, much faster for checking a single certificate. There's also certificate pinning, where a browser or application remembers the specific certificate it expects to see for a particular website on subsequent visits, making man-in-the-middle attacks harder.
Real-time check with OCSP is better. And this whole system of CAs, certificates, revocation checking, that's the PKI.
Exactly. Public Key Infrastructure, PKI, is the entire framework, the policies, procedures, hardware, software, and organizations involved in creating, managing, distributing, using, storing, and revoking digital certificates and managing public keys. It includes the CAs, RAs, registration authorities who verify identities before a CA issues a cert, validation authorities for OCSP, certificate databases, the whole ecosystem. The CA is the ultimate root of trust in a PKI.
The machinery behind digital trust. We started the section saying key management is paramount. What activities does it cover? It sounds like a lot.
It is a lot, and it's critical. Key generation. Keys need to be created securely, usually using strong random number generators. They need to be truly random and use the full possible key space. Asymmetric keys need to be much longer than symmetric keys.
Random and long enough.
Key distribution.
Yeah.
Securely getting keys where they need to go. We saw the challenge with symmetric keys out of band needed. Asymmetric public keys are easy to distribute, but private keys must be protected. Sometimes keys are encrypted with other keys.
Yeah.
Key wrapping using a key encrypting key or key K for distribution.
Wrapping keys in other keys.
Key storage. Hugely important. Where are keys kept? You don't want them in plain text files. Ideally, they're stored in secure hardware like a TPM chip on the motherboard, or even better, a dedicated hardware security module, HSM, a specialized tamper-resistant device built just for managing cryptographic keys.
HSMs for serious key protection.
Definitely. Then there's key change rotation. Policies on how often keys should be replaced. Key destruction disposition. Securely getting rid of keys when they're no longer needed or compromised. Especially important with cloud data. If you encrypt data in the cloud, how do you make it unrecoverable later? One method is crypto shredding. Securely destroy the key and the encrypted data becomes useless garbage.
Destroy the key to destroy the data.
Essentially, yes. And key recovery. Sometimes you need a way to get a key back if it's lost. employee leaves. Techniques include split knowledge, dividing the key among multiple people, dual control, requiring multiple people to authorize recovery, or key escrow. A trusted third party holds a copy of the key.
Planned ways to recover lost keys. And Kirchhoff's principle.
A fundamental idea attributed to August Kirchhoff back in the 19th century. It states that a crypto system should remain secure even if everything about the system, except for the secret key, becomes public knowledge.
Don't rely on keeping the algorithm secret.
Exactly. Assume the attacker knows the algorithm, knows how the system works. The only thing they don't know is the specific secret key being used. Focus all your security effort on protecting the key. This allows algorithms to be publicly scrutinized and analyzed, which actually makes them stronger over time.
Security through openness of the algorithm, secrecy of the key. What about SMIME?
SMIME, Secure Multipurpose Internet Mail Extensions. It's a standard for adding cryptographic security to email. It uses PKI, digital certificates, to provide authentication, non-repudiation of origin, message integrity, using digital signatures, and confidentiality, using encryption. It basically layers those crypto services onto standard email.
Securing email with signatures and encryption. Finally, let's briefly touch on cryptanalytic attacks. How do attackers try to break this stuff?
Lots of ways.
Yeah.
Man-in-the-middle attacks, where the attacker sits between two parties and relays messages, potentially reading or altering them. Replay attacks capture legitimate encrypted messages and send them again later. Pass the hash uses stolen password hashes to log in without the password. Attackers might look for keys carelessly left in temporary files or memory.
Exploiting system weaknesses.
Right. Implementation attacks don't break the algorithm itself, but exploit flaws in how it was coded or used in a specific piece of software or hardware. Side channel attacks are more advanced, monitoring things like power consumption, timing variations, or electromagnetic emanations from a device while it's doing crypto operations to try and deduce the key.
Physical analysis to get secrets. Wow.
Yeah, quite sophisticated.
Yeah.
Others include dictionary attacks, trying common words against passwords or keys, birthday attacks, exploiting probability to find hash collisions faster than brute force, and good old social engineering, just tricking someone into revealing their key or password, purchase key attack, rubber hose attack being the extreme threat version. There are attacks specific to protocols like Kerberos. Ransomware is a huge issue now, often using strong crypto to lock your data and demanding payment. And fault injection attacks deliberately introduce errors into a system to see if it reveals vulnerabilities.
A scary list of ways things can be broken. That's a deep exploration of crypto. Let's move to the final section. Section 6, physical security. Securing the actual environment.
Absolutely critical. Physical security is the foundation. It complements all the logical, technical controls we've talked about. It's about protecting assets, equipment, data, people from the perimeter inward.
Protecting the physical space.
Right. And the ultimate goal always is protecting human life and safety. After that, it's about ensuring the confidentiality, integrity, and availability, CIA, of your physical assets.
People first, then CIA for the stuff. What are the main physical threats?
Things like theft, stealing laptops, servers, backup tapes, espionage, planting bugs, stealing documents, dumpster diving, finding sensitive info thrown away improperly, social engineering, tailgating someone through a secure door, talking your way past a guard, shoulder surfing, watching someone type a password or PIN, and environmental threats, HVAC failure, causing overheating, power outages, fire, flood.
Malicious acts and environmental hazards. Does physical security also use layered defense?
Oh, definitely. It's a core principle here, too. You want multiple layers of physical controls, starting from the property line and working your way in towards the most sensitive assets. Think fences, then building walls, then locked doors, then maybe secure racks inside a data center. Each layer slows an intruder down. And the material makes a good point. Generally, the fewer entry points you have into a building or area, the easier it is to secure and monitor them.
Fewer doors are better. How do you design these controls? Starts with site surveys.
Yeah, site survey is basically a physical risk assessment for a specific location. You look at the potential threats, crime rates, natural disasters, identify the valuable assets you need to protect there, people, equipment, data, and analyze the facility itself, construction, layout, surrounding area. This helps you figure out where the biggest risks are and where to focus your controls.
Assessing the physical risks. Are there specific high-value areas needing extra protection?
Typically, yes. Inside a building, you'll have areas like server rooms, data centers, wiring closets where network connections terminate, media storage rooms for backups, maybe evidence storage if applicable, and any restricted work areas where highly sensitive processing occurs. These need stronger controls than, say, a general office area.
Like physical crown jewels, how do you secure the perimeter or the first layer?
Perimeter controls include things like landscaping, keeping shrubbery trimmed low so people can't hide, ensuring clear lines of sight, grading, sloping the ground away from buildings to help with drainage, and maybe make approach harder. Fences, gates, and bollards, those short, sturdy posts that stop vehicles from crashing into buildings or sensitive areas. And again, minimizing the number of gates makes monitoring easier.
Barriers and visibility outside.
Yeah.
What about physical detection controls, seeing what's happening?
CCTV, closed-circuit TV, is a primary one. It acts as a deterrent, provides evidence after an incident, and allows real-time monitoring. Key considerations are camera placement, no blind spots, image quality, good enough for identification, and making sure the video feed itself is securely transmitted and stored.
Cameras watching.
Also PIR devices, passive infrared. These are motion detectors that sense changes in infrared heat, like a person walking by. They need careful placement and calibration as they can be affected by sunlight or temperature changes.
Sensing movement. And lighting.
Good lighting, especially outside, is crucial. It deters intruders, improves safety for legitimate personnel, and significantly helps CCTV cameras get usable images at night.
Light things up. Doors are obviously key entry points.
Absolutely fundamental. Security depends on the door's material, steel versus wood, the strength of the frame it's set in, and importantly, hinge location. Hinges on the outside of a secure door are a major weakness. Just pop the pins and lift the door off.
Hinges inside. Good tip. What about man traps?
A man trap is usually a small room or turnstile with two interlocking doors. You have to authenticate to get through the first door. It closes behind you. Then you authenticate again or just get let through to open the second door into the secure area. Only allows one person through at a time, prevents tailgating or piggybacking.
One person at a time through the airlock. And locks.
Locks are important, but remember they are primarily a delay mechanism. Given enough time and skill, most locks can be picked or broken. They buy you time for detection and response.
Slowing attackers down. Types of locks.
Lots of types. Mechanical ones like traditional key locks or combination locks. Electronic locks like keypads, proximity card readers, RFID, NFC, or biometric locks, fingerprint, iris scan. Biometrics offer high accuracy but have privacy implications. Simple card access is cheap, but cards get lost, stolen, loaned. Combining a card with a P or biometric is much stronger.
Different levels of lock security. Windows are weak points too.
Often, yes. Large panes of glass are easy to break. Detection controls for Windows include shock sensors or glass break sensors that detect the vibration or the specific sound frequency of breaking glass.
Detecting broken windows. Walls matter too.
Yeah, what the wall is made of matters. Standard office drywall is easy to punch through. Concrete or reinforced walls are much tougher barriers. Wall height also matters for preventing climbing over.
Stronger walls are better. ATM skimming. That's physical theft too.
Definitely. ATM skimming is where criminals attach fake card reader overlays or hidden cameras to ATMs, gas pumps, point-of-sale terminals to steal credit debit card numbers and PINs. Anti-tampering designs on legitimate card readers help combat this.
Watch out for fake readers. Okay, let's talk infrastructure support systems. Power, cooling, fire, the essentials for keeping things running.
Absolutely critical. Call it power, ping, and pipe. Without reliable power, everything stops. Mitigations include UPS, uninterruptible power supply systems, basically big batteries that provide short-term power during brief outages or sags, allowing systems to shut down gracefully. And generators for longer outages, providing sustained power. Important that generator power is clean and stable for sensitive electronics.
UPS for short gaps, generators for long ones. What kinds of power problems happen?
You can have a fault or blackout, total loss of power. A sag or dip, brief drop in voltage. A brownout, longer-term low voltage. A spike, very short bursts of high voltage. Or a surge, longer period of high voltage. Spikes and surges can damage equipment.
Different ways power can go bad. What about HVAC? Cooling.
HVAC, heating, ventilation, air conditioning, is vital. Equipment, especially dense servers in a data center, generates a lot of heat and needs constant cooling to prevent overheating and failure. Maintaining proper humidity is also important. Too dry increases static electricity risk. Too humid can cause condensation and corrosion. Air quality matters too. Data centers often use positive pressurization, keeping the air pressure inside slightly higher than outside, so air always flows out when a door opens, preventing dust and contaminants from entering.
Keep it cool, stable, and clean. And fire, big physical risk.
Huge risk. Remember the fire triangle? Fuel, oxygen, heat. Remove anyone, and the fire goes out. Physical security involves prevention, good housekeeping, proper storage, detection, smoke detectors, heat detectors, flame detectors, and suppression, putting the fire out.
Different ways to put fires out.
Yes, especially important in tech areas. Water-based systems, sprinklers, are common. Wet pipe systems always have water in the pipes. Dry pipe systems hold water back with a valve until a detector triggers, good for areas prone to freezing. Pre-action systems require 2 triggers, like a smoke detector and heat, before releasing water, reducing accidental discharge risk. Deluge systems dump large amounts of water quickly over a whole area.
Water systems, but water and electronics.
Exactly, not a good mix. That's why gas-based suppression systems are often used in data centers and server rooms. They use inert gases, like hydrogen, argonite, or chemical agents, like FM200, that suppress fire without harming electronic equipment, and usually without harming people. Those CO2 systems are effective but displace oxygen, making them dangerous for occupied spaces.
Gas for the server rooms. And fire extinguishers. Different types for different fires.
Yes, absolutely crucial to use the right type. They're classed. Class A is for common combustibles, wood, paper, cloth, use water, foam, dry chemical. Class B is for flammable liquids, gasoline, oil, use CO2, foam, dry chemical. Class C is for electrical fires. MSD, use non-conductive agents like gas, CO2, dry chemical, never water. Class D is for combustible metals, magnesium, titanium, needs special dry powders. Class K is for commercial kitchen fires, grease, oils, uses wet chemicals. Using the wrong type can be ineffective or even dangerous.
Knowing your fire classes and extinguishers is vital. That's a really thorough look at physical security, the tangible layer.
It truly is the foundation. If someone can just walk in and grab your server, all the fancy logical security doesn't mean much.
Wow, okay. We have covered an incredible amount of territory today. Seriously, from those foundational secure design principles and risk management.
Yeah, least privilege, defense in depth.
Through the abstract security models like Bell-LaPadula and Biba, the evaluation criteria like comment criteria.
And that ELL complexity trade-off.
Right. Then digging into system capabilities, subjects, objects, kernels, virtualization, TPMs.
Then finding and fixing vulnerabilities, SPOFs, 2COU, hardening, mobile risks, cloud complexities, those web attacks like XSS, CSRF, SQL injection.
Then that huge section on cryptography, symmetric, asymmetric, hashing signatures, PKI, the absolute criticality of key management.
That's all the ways attackers try to break it.
And finally, wrapping up with the essential physical security layer, site design, perimeters, detection, infrastructure support. It's just vast.
It really shows that building, engineering, and operating secure systems isn't just one thing. It's a complex, deeply interconnected challenge. You really have to pay attention to every single layer because attackers will look for the weakest link anywhere.
Absolutely. It drives home that security isn't a product you buy. It's a continuous process, a system of defenses working together. So here's something to think about. Consider how these principles we discuss, things like defense in depth or zero trust or even just basic physical security for your devices. How do they apply not just to giant corporate systems, but to securing your own personal digital life? Your phone, your laptop, your home network. Does understanding all these layers maybe change how you think about protecting your own information?
That's a really powerful takeaway. How does this apply to you? Something everyone really needs to consider in today's world.
Indeed. Well, thank you for exploring this incredibly detailed domain with us today. We really hope this conversation helps you navigate the complex world of security architecture, engineering, and operations.